So we will continue our discussion on angle modulation today, and if you recollect, we had looked at the spectrum of an angle modulated signal when it is modulated by, when the modulating signal is a pure sinusoidal signal, right. That was the point at which we finished last time. So let me recapitulate. We wrote an expression for x of t, which was a modulated signal, in terms of a series expansion, right. We showed that this kind of angle modulated signal, which could have been either, which could be either an FM signal or a phase modulated signal, right. We could write this in terms of a series expansion in which the coefficients of the series are the Bessel functions, right, and the functions involved here are sinusoids of frequency omega c plus minus n omega m. So that is a series expansion for the FM signal or the PM signal, right. And how did we arrive at this? We arrived at this by considering the Fourier series expansion of e to the power j beta sin omega mt, then considering the fact that the required signal is nothing but the real part of e to the power j omega ct into e to the power j beta sin omega mt, right. So we expanded e to the power j beta sin omega mt into its Fourier series and then took the real part of that, and that is what you get, right. Now this is the starting point for our discussion regarding the spectrum of an FM signal. Of course, please remember that we are doing this spectrum discussion for the very special case when the modulating signal is a sinusoid, not for the general modulating signal m of t, right. That is a much more difficult exercise, right. So what do we find? First of all, before we discuss any further, of course this is obvious from this expression that we have a very large number of frequency components, unlike the AM case where the frequency components were omega c plus omega m and omega c minus omega m. We have a very large number of spectral components present here, right, and the behavior of the spectrum is dictated by the behavior of these coefficients, which are Bessel function values, right. So to understand the spectrum better, we need to understand a little bit about the nature of these Bessel functions. Now this is not a course in mathematics, so I will not really go into a mathematical discourse on Bessel functions. I will just give you a few salient properties of Bessel functions which are relevant to our discussion, okay? And I hope you learn it in more detail in maths if you have not already done so. So let us review some useful facts about Bessel functions. First, there is a kind of symmetry in these functions as a function of n, right. You can in the series expansion you have n going from minus infinity to plus infinity, right. Now it can be shown that j n beta is equal to minus 1 to the power n into j minus n beta. So this is how the Bessel functions with of order n and order n minus n are related, right. What this means is this is equal to j n beta or j minus n beta for n even and equal to minus of j minus n beta for n odd, right. So alternative coefficients on the positive and negative side are symmetrical but opposite in sign, right. So J1 beta and J minus 1 beta have opposite signs, but J2 beta and J minus 2 beta have the same sign, right, and so on and so forth. So that's one interesting property of these Bessel functions. The second one is, and this should be intuitively clear but mathematically can be also proved, that if you take the square of each of these functions and add it from minus infinity to plus infinity for any value of beta, right, this is equal to, it cannot be 0, we are adding sum of squares, this is equal to 1. It should be obvious. Now let us see why it should be obvious. Look at these two expressions. If you look at the power in the signal, what is the power here? A square by 2. What is the power in the signal here? It is it will be the, every sinusoid that you have in the signal has a power a square into jn square beta by 2, and obviously they represent the same signal, so the total power must be the same, right. So it's obvious that this kind of property must be satisfied, irrespective of the FM case, of course, under which we are carrying out this discussion. This can be shown purely as a property of the Bessel functions themselves. Of course, it is consistent with what we expect in our case. Okay? So that is one. Thirdly, for beta, which is, remember what is beta? Beta is this index here that is present in the modulated signal, and we have defined beta to be the so-called modulation index for angle modulated signals, right. Beta is equal to kp times am for the case of phase modulation and k sub f times am upon omega m for the case of frequency modulation, right. But nevertheless it is a factor which has some very important relevance to the present discussion, which we will come to very soon, and we call it the modulation index, right. So beta is a modulation index, and when the modulation index is very small, that is much less than 1, then all the coefficients that we are referring to, the Bessel functions that we are referring to, have a small argument. We are talking of jn beta, j0 beta, j1 beta, etc., with beta the argument being much less than 1, right. Under these conditions, the term j0 beta is the predominant term, it is a dominant term, right. So this dominates or predominates, right. What it means is, let me be more specific, j0 beta for beta very small is approximately 1, in fact j00 is equal to 1, right. So j0 beta is approximately equal to 1, j1 beta is approximately equal to beta by 2, and jn beta is approximately equal to 0 for n greater than 2, greater than or equal to 2, let us say. What does this mean? That when your modulation index is small, out of all this infinite number of terms that this expansion has, only 3 terms will be the most significant, one corresponding to n equal to 0, one corresponding to n equal to 1, and n equal to minus 1, right. That means the spectral components that you will see will be primarily the carrier frequency, which is for n equal to 0, and omega c plus omega m and omega c minus omega m. Now which is very interesting, because it is precisely these spectral components which are present in the AM signal, right. So when the modulation index is very small, the spectrum of the FM signal is very similar to that of an AM signal. There are some important differences which we will come to, right. So we call this kind of a FM signal or PM signal as narrow band angle modulation. Anyway, right now I am not I am discussing only the Bessel function properties. We will come back to this point separately again. So these are things that you can prove, that J0 beta approximately is equal to 1 for beta very small, beta much less than 1. J1 beta is approximately equal to beta by 2, and Jn beta is 0 for n greater than or equal to 2. Lastly, or may not be, maybe a couple of other properties are there. This is not of any immediate physical relevance, but one important interesting mathematical property that Bessel functions satisfy is an iterative relationship that they have with respect to each other. Bessel functions of different orders satisfy a recursion, right? And that recursion is given by this. Which essentially means that if I know Jn beta and Jn minus 1 beta for a given value of beta, I can find out Jn plus 1 beta, right? So there is a recursive relationship that is satisfied by the Bessel functions, right? So which is helpful in the computation of the Bessel functions, right? Now, but still, I think with the help of these properties you get some idea, but not a complete idea as to what the Bessel functions actually look like. It will be interesting to also plot some of these functions, that is J0 beta, J1 beta, etc., and see what they look like, and that you will start feeling better about these functions. And if you have done that for you here, and this is what the plots look like. I have plotted here J0 beta as a function of beta, right? J1 beta as a function of beta, J3 beta as a function of beta, right? And similarly you can plot more, right? So this is, so what do you see? You see that these functions are oscillatory in nature, right? They are not monotonically increasing or decreasing, they are oscillatory in nature, right? It's not exactly an oscillation of constant amplitude. The amplitude decreases as beta increases, right? And as beta becomes very large, they all become very small, right? Second, the property that we discussed, J0 beta is approximately 1, this point is 1, in the neighborhood of 0, right? At 0 it is exactly equal to 1, right? And all other functions start from 0, right? They are 0 at beta equal to 0, and they are very small. As you can see, J1 beta approximately increases linearly at this point, whereas this is not even linearly increasing. This is more or less 0 for quite some fraction of value of beta, right? So all the properties that I just mentioned to you can be seen to be true here, right? And because these functions are oscillatory in nature, the spectrum varies a lot, right? For example, let's look at this. It's for a small value of beta, the carrier component is the largest, right? And there is of course the first sideband components, that is the omega 0 plus minus omega m components, right? But suppose the modulation index is somewhere here, that is beta is equal to 2.4 or something, right? For this value, what happens to J0 beta? It becomes 0, right? So for a particular modulation index like beta is equal to about 2.4, the carrier component becomes 0, right? J0 beta is the coefficient of the carrier component, right? Remember this expression that we had? Look at this expression. When n is equal to 0, you get the carrier component. So J0 beta is the coefficient of the carrier component. This becomes 0 whenever beta takes a value such that this becomes 0 here, right? Or for example, beta is equal to 5 point something here, right? So for these values, the carrier component disappears and you have all the energy present in the side bands only, right, whereas for large values of beta energy is equally distributed in the various side bands and a very large number of side bands, right, because they all decrease. So that's so I hope with this picture you have a better feel for the Bessel functions. What do they look like as a function of beta? And if you were to use this in association with our discussion earlier, a typical spectral plot of an FM signal would therefore look like this, right. This is the frequency axis where I have chosen the frequency axis to be normalized one. I have looked at the frequency deviation from the center frequency Fc normalized with respect to the modulating signal frequency F sub m, right. So when I say this point being 0, that means F is equal to Fc here, right. So here for this point we are looking at the spectral component at the point where the deviation is Fm, F minus Fc is equal to Fm, right. So basically this component denotes Fc plus Fm and this component denotes Fc minus Fm. I have written 0 and minus 0, 1 and minus 1 here, but remember that the center frequency actually denotes the frequency, the point 0 denotes the frequency F sub c, right, because I have normalized it by subtracting it from Fc, subtracting the value of Fc from F, okay. And then so this denotes the component at the carrier frequency, this denotes the component at Fc plus Fm, this denotes the component at Fc plus 2Fm, Fc plus 3Fm and so on and so forth. Similarly these are the components at Fc minus Fm, Fc minus 2Fm and so on and so forth, right. So this is what a typical plot might look like. So as you can see J1 beta and J minus 1 beta are have opposite signs, but J2 beta and they have the same sign, J minus 2 beta and J2 beta have the same sign. Similarly for J3 beta and minus J3 beta, they have, J minus 3 beta has opposite sign of J3 beta, right, and so on and so forth. So you see a very large number of spectral components present, right. It's a wideband signal. So in general when beta is not small, right, it is a we call it wideband angle modulation, right. So this becomes wideband angle modulation. So although you had your modulating signal contain only a single frequency component F sub m, your modulated signal has a very large bandwidth, right. Any questions so far? So I think with this discussion, A, you should be reasonably clear about what Bessel functions are like and some of their important properties, and B, a typical spectral plot of, you appreciate now what is a typical spectral plot of an angle modulated signal, right. Unlike only the three line spectra that an AM signal has corresponding to this situation, the FM or PM signal will have a large number of lines corresponding to just the presence of a single frequency modulating signal at the input, right. So that's the important point. Any questions before I proceed further? No? Good, let's proceed further then. So these are some of the important properties of Bessel functions and this is what they look like. Based on this, let me summarize what are the important spectral properties we can derive. So the spectral properties which are implied by these properties of the Bessel functions are as follows. So first point, we see that the spectrum contains the carrier in general plus an infinite number of sidebands, right, not just two sidebands like we had earlier, both on the positive side as well as on the negative side with respect to Fc. Then by infinite number of sidebands I mean frequency components like Fc plus minus and Fm, unlike for the case of AM where we had only Fc plus minus Fm. Second, relative amplitudes and number of significant sidebands, number of significant spectral components. What will they depend on? Would depend on the value of beta, the modulation index. Like we saw, for a small modulation index, carrier has the largest component, other components are much smaller. But as beta increases, there can be some values of beta where the carrier component is 0 and all energy is contained in the sidebands. So which component has how much amplitude relative to each other will be decided by the value of the modulation index, right. So it depends on beta. Thirdly, we have seen that for beta much less than 1 only the first two terms are significant, or three terms, J0 and J1 are significant. And the spectrum is similar to that of AM. While it is similar, it is also slightly different. In what way it is different? That's right. The two sidebands are a phase reverse with respect to each other. There is the negative sign of one with respect to the other, right. Fc plus Fm has some amplitude and Fc minus Fm has a negative amplitude, which means it is phase shifted by 180 degree, right. So except for the phase reversal of the lower sideband component. Right, and this is called narrow band FM. So narrow band FM, which is the FM defined to arise when beta is very small, has a spectrum similar to that of an AM signal, right, in the sense that it has only the same two sidebands, Fc plus minus Fm, with this difference. As against this, when beta is large, let us say very large, the number of significant spectral components is very large. Right, and such a signal is said to be wideband FM or wideband PM. It could be narrowband PM and wideband PM, right. So large bandwidth, this implies large bandwidth. But these descriptions of bandwidth are qualitative, right. Small or large is qualitative. A natural question arises, can we convert this into a quantitative value? Can we say this is the bandwidth, right? Now that's a slightly tricky situation here. Why? Because theoretically, no matter what the value of beta may be, whether it's small or large, theoretically how many components are present in that series expansion? Infinite. So theoretically the bandwidth is, or quantitatively the bandwidth is always infinity, right? But for all practical purposes, because we have seen the nature of those functions, these functions keep on decaying as beta tends to 0. Similarly, if you look at the value of the functions for different values of n, right, I haven't got a plot here against n, but you can see the trend here. you can see J0 beta starts with the largest amplitude, right. J1 beta has a smaller amplitude, J3 has an even smaller amplitude, and so on and so forth. Similarly, the other functions will also be much smaller amplitudes each, right. So you will also find that for larger and larger values of n, the corresponding coefficients become smaller and smaller, right. So therefore it can be expected that beyond a certain value the amplitudes of these spectral components and therefore the energy contained in these spectral components would be small, and therefore they would not contribute significantly to the total energy of the signal, right. So based on this fact we need to define bandwidth in a particular way and then come up with a quantitative figure for the expression for the bandwidth, right. So let's do some discussion on that, right. So we like to look at the bandwidth of angle modulated signals more quantitatively now rather than only calling it large or small. So as I said, strictly speaking the bandwidth is infinity. But I just said that in practice we make use of this fact that limit of J and beta as n becomes large, right, this tends to 0. This is again a property of the Bessel functions which I perhaps should have mentioned when I made the list of these properties. The J and beta as n tends to infinity, that is Bessel function of infinite order identically is 0, right. So how do we define the bandwidth? To define the bandwidth, let me first define a ratio E sub r which I will call the power ratio in this manner. Suppose I consider k sidebands on either side of f sub c, right, and look at the energy contained in these 2k plus 1 components, right, from fc minus kfm to fc plus kfm. Look at the energy in this part of the signal. This is approximating the actual signal, right, and take the ratio of this energy with the total energy of the signal, right. So that I am calling either energy ratio or the power ratio, depending, actually power ratio is a more appropriate term. So what will be the power contained in the 2k plus 1 components that I just mentioned? It will be half AC square sigma j n square beta, n going from minus k to plus k, right, and the total power is half AC square, right. So as you can see, this you can write as J0 square beta plus twice of Jn square beta, beta going from n going from minus k, sorry, n going from 0 to k, because I have taken twice of this number of terms. I am sorry, this should be 1 to k, because 0 I have taken out. Thank you. So now the way we define the bandwidth is as follows. We say, we agree that for a signal to have this bandwidth, whatever we define the bandwidth to be, it should have most of its energy in that band, right. Only thing we need to now quantify is what is the definition of most, right. So we can take some arbitrary figure, and a generally accepted figure is 98% bandwidth, right. So the way we define 98% bandwidth of any signal is, particularly signals which otherwise have infinite bandwidth, right, is that band, those band of frequencies over which the signal contains 98% of its power. That means the value of this power ratio is 0.98. Okay. So basically what you need to figure out is for what value of k this turns out to be about 0.98, right, because this ratio can at most be 1. So the value of k for which this becomes about 0.98 would be the 98% bandwidth of this signal, right. So for a given application bandwidth is defined for a specific value of PR, right, and for whatever value that you select the bandwidth will then become 2k times f sub m, right. Whatever value of k would give you that value of PR would then imply that the bandwidth is 2k f. So for PR to be greater than or equal to 0.98, that is the 98% bandwidth. Now if you look at the table of Bessel functions, a very interesting fact comes to light, right, that if you choose PR to be greater than 0.98, the value of k that you need so that this becomes 0.98 depends on the value of beta, right. And but there is a very nice closed form. Of course it's not closed form in mathematical sense, it's in empirical sense. Empirically it is found that for a given value of beta, if you choose k to be equal to 2 beta plus beta plus 1, just one more than the value of the modulation index, right, that value of k would lead to this being 0.98 or larger, right. So this is something that you look at empirically from the table of Bessel functions. I can't prove it mathematically here for you, maybe it can be even proved, but I think we will just take it as that. So for PR greater than 0.98, it is noted that k can be taken as an integer part of beta plus 1. Okay. So this is an empirical result by looking at the nature of the Bessel functions, right, and therefore that tells us quantitatively the value of the 98% bandwidth. So this implies that the bandwidth is twice into beta plus 1 times Fm, right, because the bandwidth is 2k Fm, right, and that is the expression for bandwidth of an FM signal approximately. So as you can see there is a very simple closed form result here, but this simple closed form result is for the special case when the modulating signal is a pure sine wave, right. This result is valid only for that special case. Any questions? Can you give a let's give another meaning to this formula. Can you interpret what beta FM is? If you look at the expression for the FM or PM signal that you have, can you give some physical meaning to the term beta times FM? Let's go back to this expression. Yes, let's look at this expression. This is the expression for the PM signal, right. Can you give some physical meaning to the term beta times FM or beta times omega m? How will it arise? If I differentiate the argument, right, and what does the differentiated argument give me? The instantaneous frequency, right. So if I differentiate, what do I get? Omega c plus beta omega m cosine omega mt, right. Now can you give me a physical meaning? Maximum value that the signal will have of frequency deviation, right, because the frequency deviation expression becomes beta times omega m into cosine omega mt. Maximum value of cosine omega mt is 1, right. So the maximum value of the frequency deviation would be beta times omega m, right. So beta times fm is nothing but the maximum or the peak value of the frequency deviation that this signal will exhibit. You understand the definition of frequency deviation, right, with respect to the center frequency. The instantaneous frequency of both your FM signal and PM signal keep on varying or fluctuating about the mean value, which is the carrier frequency value, right. At different times you have different instantaneous frequencies, right. Remember the plots that we made for the FM signal. At some points along the axis, time axis, the signal was highly compressed where the instantaneous frequency was large, and at some other points the signal was much more sparse, and there the instantaneous frequency was smaller than omega c. The peak value of the frequency instantaneous frequency deviation is equal to beta times fm, right. So please remember that. So therefore you can also write this formula in a different way, namely twice beta times fm is, let me call this delta f plus fm, where delta f is defined as beta times fm and can be interpreted to be the peak value of the frequency deviation, peak frequency deviation. Or maximum frequency deviation. Now this analysis that we have just done is valid only for sinusoidal modulating signals. For more general signals, it's approximately possible to argue out the bandwidth of the FM signal, right. We will not go through that argument because it's beyond the scope of our course here, but I'll just give you the result. So we are looking now at the result for a general modulating signal MT, and MT is not cosine 2 pi FMT, right. What can we say about the bandwidth of the FM signal? And I'm only giving you the result, we are not going through any discussion for this. To do that, let me define D as the following ratio: peak frequency deviation upon bandwidth of MT, because MT now is a general signal, it's not a sinusoidal signal. The only way you can characterize it is through its bandwidth, right. So let me call this as delta f upon W. Delta f is the peak frequency deviation of the FM signal or the PM signal. W is the bandwidth of the message signal MT, right. Then it can be shown that approximately the 98% bandwidth of this signal, or the FM signal or the PM signal, is now given by 2 into D plus 1 times W. Very similar to the formula that we had just a few minutes ago, which was 2 into beta plus 1 times FM. And here also you can write this as delta f, isn't it? D into W is delta f plus W, and here also you can write it as 2 delta f plus f sub m, right. This is what we derived. This is a generalization of this to arbitrary signals. It's very similar, right. These formulas for the bandwidth were given by a gentleman called Carson, and therefore these are known as Carson's formulas for the bandwidth of an FM signal. Any questions? Now again in these general cases also you can see that whether you will have narrow band FM or wide band FM will really depend on the value of delta F. That's another way of looking at it. When beta is large, delta F is large, right, and you have wide band FM, right. So the important point is when delta F is large, the bandwidth will be governed largely by the peak frequency deviation, and that makes a lot of intuitive sense if you think about it, right. What you are saying is the bandwidth will be essentially dictated by what is the highest instantaneous frequency in the signal. Is it clear? On the other hand, when delta F is small, which is essentially will happen when beta is small, when the modulation index is small, the bandwidth will be dictated by the highest frequency component present in the modulating signal, right, because then it is like an AM signal. Is that clear? The signal is not like an AM signal. I am sorry, I shouldn't have said that. The signal is very different from that of an AM signal. For example, the AM signal has amplitude variations. This signal will never have amplitude variations, right, but when beta is small, its spectrum looks like that of an AM signal. Okay. So that's essentially a very brief idea about what the spectrum of an FM signal is like. Any questions? You can take just a minute if you have any questions and absorb everything that we have discussed. Hmm?
So is this method suitable for frequency sensitive operations? Frequency sensitive application. Like if we want a small frequencies also.
I'm not clear about your question. His question is this method suitable for frequency sensitive applications? Your question, should I rephrase it as should FM or PM be used in frequency sensitive applications? I don't know what that question means, so I can't really answer it. Maybe.
Which can vary with instant of time. So what he exactly means to say is if it is frequency sensitive, then I will have a disturbance because I can't exactly tell what the frequency is at a point of time.
You see, if you are referring to the process of modulation and demodulation, the value of the modulation index in some sense reflects that sensitivity that you are referring to, but the sensitivity is with respect to the amplitude of the modulating signal. Please remember that. Our purpose is fully satisfied if our modulation is sensitive to the amplitude of the modulating signal, instantaneous amplitude, and that's what we are doing in FM or PM. We are making the instantaneous phase or instantaneous frequency depend on the instantaneous amplitude of the modulating signal. So if we have, right now we are only looking at the spectral properties, right? We need to look at the demodulation of these signals so that we can see whether or not we will be able to recover those signals properly. Our concern should be with respect with the recovery of these signals, right? And the recovery process will depend on how you demodulate, right? So I think your question therefore is not relevant to the discussion that we have right now, but we are going to come to generation and demodulation of FM signals now.
So when we are using Bessel functions,
right,
so to analyze the signal, so this is only valid when the signal MT is a cos omega t signal.
That's right.
So we can't use this for in general signal.
That's right. Right? I mean, we didn't use Bessel functions deliberately. They arose. We did a Fourier series extension of e to the power j beta sin omega mt, and the Fourier coefficients turned out to be j and betas.
And so these Bessel signals are only in integers, right? And it has to be an integer.
No, Bessel functions can be defined for other values of n also, which are non-integer values, but we don't need them here. For our discussion, we don't need them here, right? There are various kinds of Bessel functions. This is only one kind, right? The various kinds of Bessel functions. So I think for that I'll like you to refer to a book on mathematics, right? Okay, then let's proceed further. If there are no more questions, next thing what we like to take up is how do we generate and how do we demodulate angle modulated signals. Obviously that's the next thing that we need to discuss. So generation and demodulation. Now, primarily there are two. Let's first look at the generation issue. Generation, right? You can classify the various possible methods into two broad categories: the direct methods and the indirect methods, right? The direct method actually uses a device. What do we want? How can we generate an FM signal? Just think about it. How do we generate a sinusoidal carrier? What do we need for that? An oscillator of suitable frequency, right? Now what do we want? We want the frequency of this oscillator to depend on the amplitude of another signal, right? So we need to modify this oscillator if we can, such that the instantaneous frequency of this oscillator can be made to depend on a voltage somewhere, right? And it's fortunately possible to design such circuits, right? And when you have been able to design such a circuit, we call it a voltage controlled oscillator, right? So the direct method basically depends on the design and construction of what are called voltage controlled oscillators. Are in short known as VCOs. Okay. Now you have voltage control oscillators of different kinds which have been designed and fabricated. Now depending on what frequency range you are working with, you will have different kinds of designs, right? You can have a voltage control oscillator based on LC components, right? You can have voltage control oscillators based on RC components, which are called relaxation oscillators, right? I do not know whether you have come across stable multivibrators in your either digital or analog electronics. If you have come across stable multivibrators, they are nothing but voltage control oscillators, right? If you are working with microwave frequencies, there are special devices like klystron, right, which can be used as voltage control oscillators, and so on and so forth, right? Now since therefore it depends on what frequency you are working with, you have different kinds of devices, right? I will not go into a very detailed discussion of the design of the voltage control oscillators, except to say that it is possible to design circuits, devices, systems which can be essentially voltage control oscillators. And once I have such a voltage control oscillator, to the control input, basically what does it mean? That you have an oscillator, right? I mean, if you look at it purely from a block diagrammatic point of view, an oscillator normally there is no input except the power supply, right? And it produces an output oscillation signal, right? Here you have a control voltage, right? And the frequency of this will depend on the voltage applied here. So if I apply to this at the control voltage terminal the modulating signal, right, the output oscillations will depend on the input amplitude, right? That is what these devices do. As to how they are designed would be the subject of would be the topics of subjects that you are doing otherwise, right, other subjects that you are studying or will study. So we will not go into those. We will assume that such things are possible to make. Maybe we will discuss one such example slightly later. Okay, this is for what kind of oscillations will, what kind of system will this be? Frequency modulated signal or PM phase modulated signal? If I use a voltage controlled oscillator, this will give me FM or PM? Frequency modulation. Can I use it for generating PM? Just think about it. Here is a message signal MT. Good, very good. He has suggested the answer. So if I apply MT to a VCO, I'll get an FM signal. Right? This is what you are saying. Right? If I apply MT, but first differentiate it, right, and then apply to a VCO, I'll get a PM signal. You remember why? Okay, so I don't have to repeat it, but just to complete the discussion, remember that the instantaneous frequency of a PM signal would be proportional to the derivative of the message signal, isn't it? It's obvious, because instantaneous phase deviation is proportional to the message signal MT. So the instantaneous frequency deviation will depend on the derivative of the message signal, because the instantaneous frequency is derivative of the instantaneous phase, right? So this is how it comes. So if I feed MT directly to VCO, I get FM. If I feed a differentiated version of MT to the VCO, I get the PM signal, right? Actually, we will discuss later, for various reasons, what we call FM transmission is neither pure FM nor pure PM. It's something in between, right? What that means is something that we will discuss later. So I'll stop here for the moment, and next time we'll discuss the indirect methods. Thank you very much.